Hello, everybody. My name is Raj Dabre from NICT Japan, and on behalf of my co authors, I'm happy to present our work titled A Study on the Effectiveness of Large Language Models for Translation with Markup. In this talk, I'll first give a background about translation with markup and LLMs and in context learning, following which I will talk about in context learning for text with markup, where I'll talk about the prompting approaches and example retrieval approaches that we used in our work. I'll describe the experimental setup and then go into the results and analysis, where I'll discuss the impact of shorts, retrieval approaches, and model sizes. And finally, I'll talk about the human evaluation that we did. So, what is translation with markup? Note that in regular machine translation, we simply translate sentences from one language to another. But in a real life setting, we mostly do not translate single sentences, but we use machine translation systems to translate web pages. So, for example, a web page that looks like this, internally, it's going to look something like this. It's going to be in the form of some hierarchical structure. And content inside, sometimes you'll see some words which are bolded. These will be marked with some HTML or some XML tags. Now let's take an example. So suppose you have a sentence like click prepayment, where prepayment might be one word which has been annotated with this tag called UI control. Now when we translate it into Japanese, we would want the translation of prepayment to be marked with the same tag. And therefore, in translation with markup, we have to do a combined task where we have to translate as well as transfer markup tags within translatable segments to the translation appropriately. In the past, there have been two major approaches to perform translation with markup, one of them being the DTAG and project approach. If you look at the example on the right, you can see what happens is you have a sentence with markup, you remove the markup and keep the raw sentence, you translate it, you figure out the alignment between the words, and then based on the aligned tokens, you will re-inject the markup information. So the advantage is that you will have reliable markup transfer as long as you have a reliable alignment system. But the disadvantage is that there is too much of effort involved because you have to go through multiple stages, and an error in one stage will often propagate to errors in the other stage. On the other hand, a recently proposed approach is the direct translation approach, where you leverage fine-tuned LLMs as they are. So for example, Bushbeck et al., what they did was they took an M2M model and or a fine-tuned MBART model and translated sentences with markup directly. And they found out that such a system is able to handle markup transfer pretty reasonably well. So the advantage is that there is no extra effort. It's an end-to-end blind or black box system. But in their analysis, they found out that there are several cases of under and over translation because the generation process tends to be a bit uncontrolled. Noting the success of the direct translation approach, we realized that it might be possible for large language models to do end-to-end translation as well. So some background about how large language models may be useful via in-context learning. So in the previous approaches, what we used to do is we used to pre-train a model and fine-tune them. And this would be computationally expensive because we would require a huge amount of annotated data and would have a separate model for each language and task. But now, in the modern times, what we do is we take a large language model, which is pre-trained, and then what we use is called as in-context learning, where you run the model only in an inference mode, and therefore a single large language model can be used for a variety of downstream tasks. The most default way in which a large language model may be used is called as zero shot, where you simply give the model a particular task description. For example, you can say translate from English to French, and you give an English word, and then you ask it to generate. So if there is a language model that is sufficiently large and trained on a sufficiently large amount of data, it has this innate ability to perform translation from one language to another, as well as perform many other tasks like summarization. However, it's not possible for a single language model to perform any task blindly without seeing any kind of demonstrations. Enter in context learning, where we give some task description and an example. So for example, if you have translate from English to French, then you give an example translation for sea otter to its French translation, and then you prompt the model, giving the word cheese, the English word or sentence, and ask it to generate a translation. Now, because the model has seen an example of what English to French translation means, it should be able to do better than zero shot. And the extension of this is few shot, where instead of giving just one translation example or just one demonstration example, we consider multiple demonstration examples. And finally, we prompt the model for the translation for the desired sentence or word. Following the principles of in context learning, our approach was to retrieve examples from the development set, where we used examples with markup for test sentences with markup and plain examples for plain sentences. We worked with 0, 1, and few shot prompting, where in few shot settings we imply 4 shot, where 4 examples were used for prompting. The prompt template that we used was as follows, and we use these square brackets as delimiters to control stopping. We perform post-processing to remove the unnecessary delimiters, the prompt prefix, and anything after the closing bracket delimiter. As for the retrieval approaches, we focused on BM25, which is an n-gram-based retrieval approach, the embedding similarity approach using the LabSay as a embedding representation generation, and the CHRF similarity-based approach. In this paper, most of the results we talk about use the embedding similarity, and we do ablations with comparison against the CHRF and BM25 approaches. The models that we used are the Bloom and BloomZ 7 billion parameter models, and we also perform an ablation against the 176 billion Bloom model. The data set that we use is SAP's software documentation data set, where we focus on Japanese, Chinese, and Korean translation to and from English. As for evaluation, we use Blue, CHRF, and Comet metrics. In this presentation, I will only talk about Blue scores, but the other metrics are highly correlated. As for the scores that we report the raw, lex, and tag scores. And why 3 different types of scores? Because we want a multi-view evaluation in addition to human evaluation, which I'll talk about later. The raw scores give a holistic evaluation of the entire output or translation. The lex scores give an evaluation of the meaning, and the tag scores give an evaluation of tag placement, the last two being fine-grained evaluations. Now let's take a look at the main results. We report only the blue scores here. We compared the Bloom and BloomZ 7 billion parameter models in 0, 1, and few shot settings against baselines such as M2M model for direct translation and an in-house SAP system with the DTAG and project approach for tag placement. Note that the in-house system is highly optimized for the domain that we're working on. One key observation is that no matter what the language pair is, in a zero shot setting, the Bloom model tends to perform really badly. Just a note on the score format over here. For English to Japanese, 3.0 indicates the raw score, 0.2 indicates the lex score, and 13.9 indicates the tag score. The Bloom Z model in a zero shot setting performs better than the Bloom model, obviously because Bloom Z has been instruction fine-tuned. Now let's look at the one-shot scores. The Bloom model outperforms the Bloom Z model because the Bloom Z model isn't designed to handle multiple shots. And when we increase the number of shots to 4 shot, which is the few shot setting, we see that the Bloom model tends to be the best among the LLMs. However, none of these models manage to compare against the M2M and the in-house models, especially the in-house model is too strong. But we can see that in some cases, for example, English to Japanese and English to Chinese, the tag scores are almost as good as or better than the tag scores of the M2M in-house systems. So that means these LLMs have some sort of promise when it comes to handling the transfer of tags. Next, we also studied the impact of the model size for English to Japanese translation, where we introduced the 176 billion parameter Bloom model, where we observed that in a zero shot setting, it does as bad as the 7 billion parameter model. But when you start introducing more shots, like 1 and 4 shots, we can see that the Bloom 176 billion parameter model is substantially better than the one shot, than the 7 billion parameter model. Especially in a 4 shot setting, this 176 billion parameter model is at least 10 points, no matter the raw, lex, or tag scores. Note that the tag score for the 176 billion parameter model surpasses that of the in-house system, which means these LLMs definitely have promise for tag transfer. We also studied the impact of the example retrieval approach. So far, I've only talked about results using the lab say retrieval approach, but we have to understand what happens if we switch the retrieval approach. We compared English to Japanese one shot and few shot settings using the BM25, CHRF, and lab say approaches, and we didn't find any particular reason to believe that one approach is better than the other. Although LabSet does appear to be slightly better in a four-shot setting, we do not recommend that it is, we do not consider that it is better, particularly better than the other two approaches. Next, we consider the impact of ordering of examples. Thus far, we have kept the best retrieved example closest to the test set sentence, but it is possible that reversing this order might have a better or worse example, and we wanted to know exactly what that was. So we compared the Bloom and Bloom Z models for the three retrieval approaches for English to Japanese translation, and we observed that keeping the best retrieved example closest to the test set sentence being translated is always going to give better results as compared to keeping the best retrieved example at the beginning of the prompt. So therefore, we recommend to keep the most similar example or the best retrieved example closest to the test set being translated. I will now present to you the results of our human evaluation that we conducted for English to Japanese. We actually wanted to explore two different things. One is the overall translation quality, and the other is the placement accuracy for the evaluation of the tags. We use post-editing, which we consider as a reliable method to judge translation quality with the assumption that fewer edits correspond to better quality. So we selected 200 sentences randomly from our test set and had the translations without markup post-edited by two professional translators who are specialized in the domain. And the instruction that was given to them was to restrict the edits to the minimum necessary for evaluation. We selected four systems, which are the two blue models with the 7 billion and 176 billion parameters, both in few shot settings, and M2M and the in-house system to measure the quality. We use edit distance metrics, in which we consider the translation error rate and its character equivalent. Over here, lower the scores, better the quality, and the chart shows you the results. So both edit distance metrics confirm that the in-house model performs the best. It is followed by the Bloom 176 billion parameter model that has some potential to master in domain translations. While the smaller Blue model and the M2M model require significantly more post-editing. Now let's have a look at the results of the tag placement evaluation. For this, we use the same 200 sentences as in the post-editing evaluation, with the difference is that we kept the markup in the text. We asked the translators to modify the wrong tags only so that they could add or move or rename the tags that were wrong, but they were not allowed to alter the translated text. And with the output, we were able to calculate the percentage of correctly transferred tags. If you look at the chart on the left, you can see that the Bloom 176 billion parameter model is able to outperform every other system with an accuracy of 93% for correct tag transfer. It is also interesting to take a look at the errors that occur. And you can see in the chart to the right that the most prominent error is that the tag is not placeable at all. This means in the target text, there is no word or expression where the tag should be put around, and this is related to bad translation quality. It was also interesting to see that the in-house system had a problem in correctly positioning the tags in the target sentence. This might be due to the detag and project approach that was used here. And there are some other errors that might be quite serious and harmful in a production setting, like hallucinated text or wrongly named text or lost text, because they will not allow to generate well-formed documents or to render them in the structure they're supposed to be. In conclusion, we have observed that LLMs have a great potential to handle inline content. They exhibit excellent tag transfer quality as evidenced by automatic and human evaluation. The Bloom models tend to be better than the Bloom Z models, especially in few short settings. But that's understandable because Bloom Z is designed for zero shot. In the future, what we want to do is understand how few shot instruction fine tuning would work in inline translation scenarios. We want to study the impact of synthetically created shots. And we also want to ensure that a 7 billion parameter can do as well as the 176 billion parameter model, but probably via distillation. Thank you for listening.